Good morning, guys. Today we're going to finish up chapter 8 in our discussion on fluid transfer equipment as well as heat transfer. So from last time, I remember correctly, we were wrapping up some discussion on net positive suction head as it relates to preventing cavitation within pumps. And we had derived our net positive suction head equation as 1 over gravity times the quantity of initial pressure minus vapor pressure over density minus your velocity head, u squared over 2, minus any head loss in the suction line. And then correcting for the static head associated between the inlet of the suction line and the pump itself, which is designated as ZA. I had stated a couple things to keep in mind, being velocity head is often neglected from the calculation because the value you typically obtain is very small as compared to the other terms. In addition, it's important to note that even though the expression is traditionally written as minus ZA, the height is actually going to be, and the sign of it is going to be dependent on the pump location relative to the fluid level in your inlet. And so if your pump sits below where the liquid sits at the inlet, you can consider that to be positive, as you expect to have a net increase in static head. And if the pump is above that fluid level, then you can consider that value to be negative, as you would have a negative suction static head, or it requires a certain amount of lift of the fluid to get it into the pump. And then I left off with this question in terms of and analyzing the net positive suction head expression in terms of how we can use the equation in our understanding of fluid mechanics to avoid cavitation within our pump system. So what thoughts do we have? So given our expression in PSH, A equals 1 over gravity times PA minus PV over rho minus u squared over 2 minus head loss minus C sub A. How can we avoid cavitation?
I mean, probably the easiest thing to change would be that the difference in height between the fluid and your pump.
Okay, so change height. Or say change the static head. What's the best way to do that if we're thinking of it in terms of a chemical process? There are some ways to do this better than others.
Increase your tank level that you're holding.
Yeah, so you can increase the level of fluid in the tank. This would definitely be the simplest correction you can make in a process, because that's just basically changing your fluid level set point in your system, assuming a steady state. What other things can we do based off the expression?
You can change your volumetric flow rate.
All right, we can change our flow rate. So this would reduce the velocity and expected head loss. In the suction line. Any other ideas? I appreciate you guys. Go ahead.
Could we try and manage the differences in pressure, to keep that ratio down?
You could. So the easiest way that you can do that to manipulate that relative pressure ratio is you can decrease your fluid temperature. And this would reduce your vapor pressure. You could also increase your fluid temperature in the inlet. That may or may not be a little more difficult. The last thing that you may or may not be able to do is you can consider changing your suction line pipe diameter. This will also decrease your flow velocity and your expected head loss without having to manipulate your flow rate. You can keep your flow rate constant. However, sometimes it's easier said than done. Changing pipe diameter means, changing, capital. So there's quite a few ways that we can kind of tweak a fluid system to ensure that we don't have issues associated with cavitation. So any questions on net positive suction head? Or are you guys, pretty confident? You guys actually have done pretty well in terms of that. So, but if you have any questions, comments, or discussion points that you'd like to bring up, feel free. And
so when you were talking about the sign of ZA, is that including the negative sign in that term? So like when you said that like if it's below, it should be positive, is that like two negatives make the positive? Or
that's a good way to see it. It's basically, yeah, lumping that minus CA in a group and then ask yourself, should that be minus CA or plus CA? If your pump sits below, it should be plus CA. If your pump sits above the fluid level, then it should be minus CA. And I say that because a lot of times students get confused because they see the minus and they think it should always be minus. So yeah, your mindset is right in terms of how to approach that. Any other questions? All right, if not, then let's continue discussing fluid transfer equipment, and we can talk about our next section and final section, transportation of gases. And so we can typically transport gases through one of three mechanisms. We have fans, blowers, and compressors. Each serve a unique purpose, which we'll talk about now, with fans being designed to transport large volumes of gases. And the typical thing that we're not concerned with is pressure drop. So essentially a fan is designed to apply just enough pressure to get your large volume of gas from A to B, not necessarily concerned with actually trying to demonstrate a net increase of pressure on our fluid. A blower, on the other hand, is mainly designed to transport gases at high velocities. And with that, we expect and we often find moderate changes in delta P. Now, a compressor is going to be more of a workhorse as associated with chemical processing because its main purpose is to actually increase the pressure of a gas. And so we see a lot of variation in our pressure drop, but we can also achieve fairly high changes in pressure drop on the order of 1 to 1,000 atmospheres, depending on the desired change in pressure. And then that's considering if we were going to compare between compressors, fans, and blowers, a fan, pretty small, maybe 0.4 atmospheres to an atmosphere. A blower, maybe 1 to 5 atmospheres. And so you can, kind of tell that if you're wanting to see an actual increase in the pressure of your gas, you're going to be using a compressor 9 times out of 10. That's why in most chemical process facilities, when we talk about fluid transfer equipment, where we most often rely on compressors, because at the end of the day, a lot of times what we're looking at doing is changing the pressure of the fluid. With the rest, like a fan, you're just trying to move the gas from one place to another. A blower, you're trying to get it at high velocity to affect some form of heat transfer, typically over a short distance. But if you're wanting to change the fluid pressure for like a reaction or a separation, you're going to be using a compressor. And so with that, let's talk a little bit more about compressors and gas compression. Like our discussion that we had on compressible flow, we can typically put these systems into one of 3 categories: isentropic, adiabatic, and isothermal. One thing we also often consider with an isentropic compression is how increasing our fluid pressure results in an increase of fluid temperature. By fluid, I'm really talking about vapors and gases. This is unique to compressible flow. And based on our discussion that we had in chapter 6, we can identify that increase in temperature following this expression. TB over TA is equal to PB over PA to the 1 minus 1 over gamma power. Right, and once again, we had this PB, this is our pressure ratio or our compression ratio, and gamma is our ratio of heat capacities, which is going to be a constant for a particular gas. However, we don't live in the idealized world of isentropic compression. We have to consider energy losses and work associated with overcoming those losses. And so we consider the implications of both adiabatic compression and isothermal compression. So for adiabatic compression, we can calculate the work associated with that compression if I can find the right equation, as this equation here, where I can see work is equal to our initial pressure times our gamma constant divided by gamma minus 1 times our initial density times the quantity of our pressure ratio to the quantity to the power 1 minus 1 over gamma minus 1. This is equation 816 on page 220.
For adiabatic compression, what is in the denominator? Is that a P or a rho?
Can you say that again? Sorry, I got it cut out for me.
I was looking at the denominator for adiabatic compression. I'm
This
trying to
is
figure out
density. So the top
Okay.
piece of A is pressure, the bottom and the denominator. This is density.
Thank you.
Of course. And we can also calculate the power for adiabatic compression by this following equation: 0.371 if I can write it properly, times temperature times gamma times our flow rate initially divided by gamma minus 1 times our efficiency times our quantity of our pressure ratio times 1 minus 1 over gamma minus 1. Now you'll notice this one has a constant which serves to correct for some units. And so TA is temperature but it must be in Kelvin units. Q naught is your initial flow rate or your flow rate. But it has to be expressed in standard cubic meters, per second. And this provides power in kilowatts. And if you're going to look at it in terms of English units, here I'll zoom out. The equation changes slightly to 1.304 times 10 to the minus 4 TA Q naught times gamma divided by gamma minus 1 times efficiency times PB over PA times 1 minus 1 over gamma minus 1. So the only thing that really changes is that constant, this being equation 8.20b on page 221. And in this one, TA is our initial temperature. But in degrees Franken, Q naught is our flow rate of our gas. In standard cubic feet per minute. And this provides power in horsepower. So it's the same expression, it's just been corrected for unit conversions. So you can use either of these equations to solve for power in a compressor, provided you're using the proper units when you plug in.
Power on the first one, you have a K there. Is it kilojoules or joules?
I'm sorry, it's kilowatts.
Kilowatts. That makes
Thank
sense.
you. I probably tried to write the W and my pen said no thank you. So for adiabatic compression, we can solve for both the work and the power, provided we have our initial conditions and our desired compression ratio over that compressor. In addition, we can solve for the temperature we get out of the outlet using our isentropic equation, which is equation 813. So this is equation 813 on page 216. Now for isothermal compression, we have slight modification of our expressions. We're to solve for work. We get the following equation. Work is equal to R times our initial temperature over the molecular weight times the natural log of our compression ratio. And to solve for power, in isothermal compression, we have 1.304 times 10 to the minus 4 times our initial temperature times our flow rate divided by our efficiency times the natural log of our compression ratio. Where E sub A is going to be our initial temperature. Degrees Rankine. Q naught, once again, is our flow rate. In standard cubic feet per minute. And power is provided in horsepower. This being equation 820C, oh, 21B, excuse me. On page 221.
Dr. Lopez,
Yes.
what's the difference between standard cubic feet and just cubic feet?
That's a good question. So standard cubic feet and and standard cubic meters as compared to just cubic meters, it's the flow rate evaluated at a particular temperature and pressure. And so to be considered standard, it's evaluated at 0 degrees Celsius and 760 millimeters of mercury. So it's basically flow rate measured at a standard temperature and pressure. As fluctuations in that value are going to change the measured volumetric flow rate, even though the mass flow rate will be constant. And so by identifying the flow rate at that standard, calculations can be derived to consider the systems outside of that standard. So it's a way to normalize the flow rate to a standard temperature and pressure, and then derive equations that correct for those fluctuations. And it's necessary in compressible flow because temperature and pressure are going to manipulate what the expected what we see for flow rate. For incompressible flow, the pressure is not going to, and the temperature is not going to have an appreciable effect on what we see in terms of volumetric flow.
So if we were given say we were somewhere with a compressor that had some sort of instrument for reading the inlet temperature, outlet temperature, and pressures and stuff. So these equations wouldn't work for that because they're not at 0 degrees Celsius and 760.
Yeah, you'd have to correct for it to identify based off what you're reading, what would be the equivalent standard flow.
Okay, thanks.
Yep, no problem. Yeah. And so surprisingly, the book leaves off equation 821A, which calculates the power for isothermal compression in SI units, but it's just simply 1.97 times T sub A Q naught over eta ln of PB over PA. And I'll clean that up a bit. Where once again, TA is in Kelvin, Q naught is in standard cubic meters per second, and P gives you power in kilowatts. So with these equations, you can kind of get an idea of how to calculate both work and power in your systems. Now, one thing we do need to discuss is when we're considering compressors, as the fluid experiences a pretty significant increase in temperature as the gas is compressed, it's standard practice to limit the degree of compression that exists within a single compressor. Meaning if I want to have a fluid, let's say at, 15 psi, and I want to get it to 500 psi, it's extremely unlikely that you're going to be able to achieve that in one compressor. And so what typically happens is you have to have a series of compressors that can achieve your desired pressure increase. And so what that looks like can be shown on this lecture slide. Or if you see at point 1, we have feed gas going into a compressor. Then it gets heated after that compressor, so it must be cooled. Now, if there's any condensables within that gas stream, compressing it and then cooling it may result in liquid formation. And, you can just imagine if I have a stream of humid air, if I can continually compress it and then cool it, eventually I'm going to end up forming liquid water because the pressure in the system is high enough that it essentially falls out of the vapor phase. And so just like a pump doesn't like vapor in a system, a compressor typically can be damaged by liquid within the system. And so what's done is what's shown in this figure, where you have these knockout drums that separates any liquids or condensables from the gas that you're compressing. And so you have essentially a cooler, then a knockout drum to allow the next stage to continue, then another cooler, then another knockout drum. And so this is basically illustrates a multi-stage compression system to ensure, one, the temperature doesn't get too high, as well as it ensures that there is no liquid entering any of the compressors within the system. So the question is, well, if I have a multi-stage compression, how do I know the compression ratio for each stage? Well, we have minimized work or minimum work.
You're still on the PowerPoint.
Thank you. When each compressor has the same compression ratio. And so to identify both the number of necessary stages and the compression ratio of each stage, we can use the following expression. So it comes out looking like this. So I can say compression ratio for one stage is equal to the nth root of my desired outlet pressure based off the inlet gas pressure, where N is the number of compressors in the system. So if I know my desired inlet and outlet, based off of that, my expected number of compressors, I can find my compressor ratio and vice versa. And
How
we
would
typically,
you find this if you don't, like, if you don't have either of those values? How would you like determine that?
no, you'd have to rely on a rule of thumb. And so when it comes to P sub R for a single stage, the rule of thumb is you really want to limit to the extent that you essentially compress a fluid in a single stage. And so P sub R of stage 1 in a single stage should be less than or equal to 4. When you get to compression ratios be above 4, you start seeing dramatic shifts in the outlet temperature, in the temperatures, which results in, one, a lot of inefficiencies and issues associated with, having extremely high temperatures. So let's look at an example that kind of illustrates this point. So in this example, we have a 3-stage compression system being used to compress 180 standard cubic feet per minute of methane, coming in at 14 psi and leaving at 900 psi, with an inlet temperature of 80 degrees Fahrenheit. So the question is, what is the power or brake horsepower if the mechanical efficiency is 80%? And what would be the discharge temperature of the first stage? So let's take a look at this example. So we have a 3-stage compression system where the inlet pressure is 14 psi, the outlet pressure is to be 900 psi, and the inlet temperature is 80 degrees Fahrenheit, which is 540 degrees Rankine. And our initial flow rate as provided is 180 standard cubic feet per minute. So we're looking for the power given the efficiency of 80% or 0.8 and the expected temperature at the outlet of a single compressor stage. All right, so the first thing we need to find is the pressure ratio. So for this, we're going to be looking at the nth root, or since it's a 3-stage, the cube root of the outlet pressure, which is 900 psi, divided by the inlet pressure, or 14 psi. So if we take the cube root of 900 divided by 14, we should get a pressure ratio of approximately 4.
That's supposed to be PB over PA.
Yes, thank you. So for this system, since we're expecting the temperature to change, I would assume it's an adiabatic compressor. And so the power is going to be 1.304 times 10 to the minus 4 times TA Q naught gamma over gamma minus 1 times efficiency times the quantity of PB over PA, 1 minus 1 over gamma minus 1. Keeping in mind, the temperature has to be in Rankine, the flow rate has to be in standard cubic feet per minute to get the proper units for power. So luckily I have everything that I need to solve this problem. So I have power is equal to 1.304 times 10 to the minus 4 times my temperature, which is 540 degrees Rankine, times my flow rate, which is given at 180 standard cubic feet per minute, times gamma, which for methane should be approximately 1.31. Divided by gamma minus 1, or 0.31, divided by the efficiency, or 0.8, times the quantity, our pressure ratio, which we got a 4, to the 1 minus 1 divided by 1.31 power minus 1. So if we do this calculation, we should get a power of approximately 26 horsepower. Now keep in mind that power is for one stage.
Dr. Lopez,
Yes.
does that 1.304, whatever that number, deal with all of the unit conversions, like minutes to seconds and stuff like
Yes.
that, to get horsepower?
Yeah, it's essentially all the unit conversions are kind of bundled in that constant. So you're not going to be able to do any sort of checking. So you just have to make sure the values you put in terms of temperature and flow rate are the proper units.
And Dr. Lopez, the reason we put 4 in there for PB over PA is because it's only for one stage.
Yes.
Okay.
Wait a minute. I know you said that you had to put the right units in, but for this question, you put it in standard cubic feet per minute. I thought it had to be in standard cubic feet per second.
No, it's in standard cubic feet per minute for the English. And for
Okay.
SI, it's standard cubic feet meters per second.
Okay. That's what
So
I
yeah,
messed
you
up.
do
Thank
have
you.
to be careful, yes. Good questions. And so the power we obtain for one stage is approximately 26 horsepower. And so if I'm going to look at the power for all 3 stages, all I need to do is multiply that times 3. And so I obtain an approximate power for 78 horsepower for all 3 stages.
Could you explain what you would do if you were given a flow rate that wasn't already in standard cubic feet per minute?
You would have to correct the flow rates. So you'd have to basically use the continuity equation. So, you know, let's say it was 180 degrees or cubic feet per minute, but this was taken at, I don't know, 75 Fahrenheit and 1.5 atmospheres, right? So this would basically correspond to a particular density. So I could calculate this density at this condition, right? So rho sub 1. So I would say 1.5 atmospheres is what? In PSI, 14.7, 22 PSI. And then molecular weight of air, let's just say, well, it's methane, right? It's the molecular weight of methane. 20? 16. Math.
16.
Yeah. So 16 pounds per pound mole. R would be 10.73. Standard cubic feet, PSIA, per pound mole R. Temperature 75 Fahrenheit. And Rankine is 535. So if I did this calculation, I'd have 22 times 16 divided by 10.73 divided by 535. So I get a density of approximately 0.0613 pound mass per cubic foot. I would have to compare that density to the standard of 0 degrees Celsius and 1 atmosphere. So 0 degrees Celsius is what in Rankine? About 492. So I would basically compare this to a rho naught. So 14.7 psi times 16 divided by 10.73. I'm cutting off units just to make this a little faster. Over 492. So at that temperature and pressure, if I can reshare. I get approximately 0.0446 pound mass per cubic feet. Right? And so now I have two different densities. So if this 180 feet was taken with this density, right? I would have to figure out, okay, what would be the flow rate if I measured it at standard temperature and pressure? So by continuity, the flow rate is going to be the density times velocity times flow area, right? So if, or it would be, it's volumetric flow rate, so it's going to be, no, I'm right. So mass flow rate is equal to density velocity area, right? And so I know my mass flow rate is going to be the same for both systems. Right? And so basically means, since I know my volumetric flow rate is density times, or excuse me, I'm probably getting a little confused here. It's density times my volumetric flow rate, right? Because U times A is volumetric flow rate. So this basically means rho naught times V naught equals rho 1 times V1. So if I'm looking now for the standard volumetric flow rate, I would say V naught is equal to rho 1 V1 over rho naught. Or in this case, 0.613 times 180 cubic feet per minute divided by 0.0446. And now this would give me standard cubic feet per minute. And so to make this correction, and there should be a 0 there. So you'd get a value of approximately 247 standard cubic feet per minute. And so by applying continuity, you can correct for any temperature and pressure that you're doing your flow rate reading at by essentially doing a comparison of the fluid densities. So a little bit of a tangent, but hopefully that makes sense. And so now you can see taking it from a measured flow rate to putting it into those terms of standard. flow rate. Does that make sense?
Yes, it does. Thank you.
Perfect. No, you're welcome. All right, so with the last little bit of time we have for today, let's finish up this example. So we found our power, 78 horsepower for all 3 stages, based off the expression, 820B. So now we need to do is, what's the expected outlet temperature? Well, following the expression we derived earlier, TB over TA is equal to PB over PA to the 1 minus 1 over gamma. So this ratio is essentially going to be 4 to the 1 over 1 divided by 1.31. So if I do this calculation, I get approximately this equal to 1.388. And so if TA is 540 Rankine, TB is going to be 540 Rankine times 1.388. Or 750 Rankine, which is approximately 290 degrees Fahrenheit. So quite a drastic increase in temperature, going from 80 degrees Fahrenheit to 290 degrees Fahrenheit. And you can imagine, you know, what it would be, let's say if you tried to compress it straight from 14 to 900. So if you tried to basically make that happen, the temperature would actually be, let's see, of 986 Fahrenheit. So you can kind of see why it's important to operate the system in stages to avoid excessive heating of your fluid. So any questions on that example or the discussions that we've had on fluid transfer equipment for gases? We really focus on compressors because that's where the real work is going to be done, pun intended.
Hey, Dr. Lopez, I had a question.
Go for it.
Could you go back to that process flow diagram for the interstage cooling?
Of course. Let's see if my computer will let me switch. All right. Yes, go for it.
Could you explain again how those knockout drums separate liquid? Because it looks like it's all just being fed to the compressor anyway.
Well, the vapor's being fed, right?
So
but
where's the liquid going? I guess is my question.
The liquid's just going to hang out in the drum until it gets removed.
Oh, okay. That makes sense.
Yeah. So it's essentially existing as a phase separator, right? You're going to feed your mixture into it, but the liquid's not going to go up. It should settle into the drum. And so depending on how much liquid accumulates, you can just let it run until you do shutdown to drain whatever's left, or you have some sort of drain valve at the bottom of the drum that you open periodically. All right, any other questions? If not, thank you all for your attention. I do appreciate your participation and engagement today. Hopefully we can keep that going. But as I said, this is the last discussion on fluid mechanics. It's a good job. Halfway through the class course material. Hopefully you feel pretty comfortable in terms of how fluid operates within process systems. But as always, if you have questions, I will jump over to office hours in about 10-15 minutes. So feel free to come by, ask homework questions. But if not, take care, guys. Have a great day and have a great weekend. I would say, you know, go Ole Miss, beat Bama, but I'm also a realist, so we'll
Yeah, they're
see.
going to drop out 65 on us.
Yeah, I always joke because I like how everybody says beat Bama, because all you got to do is change it a little bit, and then it can just say beat by Bama with minimal effort in changing it. They're just hard to beat. Take care, guys.
Later.
Thanks, Dr. Lopez.
Have a
Thank
good
you,
day.
Dr. Lopez.
You too.
Have a good weekend.